We look at some more examples to solve LPs before we go to the formulations and try to solve those problems that we had actually formulated. So, we take another maximization problem with two variables. The two variables are x1 and x2 that are shown here, x1 and x2. Right now we give some arbitrary values, say 1, 1 to the two variables that we have here. The objective function for this problem is maximize 4x1 plus 3x2. So, 4x1 plus 3x2, I am just writing the 4 and 3 and I am just writing the objective function is equal to 4 into the value of x1 plus this 3 into the value of x2, which happens to be 7. There are three constraints, x1 plus 2x2 less than or equal to 7, that is already written here, x1 plus 2x2, 1 into 1 plus 2 into 1. Second constraint is 3x1 plus x2 is less than or equal to 11, and the third constraint is 4x1 plus 5x2 is less than or equal to 26. They have all been written here. So, now we have written the problem in the sheet and we now look at the solver. So, we go to the solver and then we set the objective function to this position, which is already set here. It is a maximization problem. The two variables are the B3 and the C3, which is already set here, and the three constraints are here, which I have already set here. So, the three constraints are B8 is less than or equal to D8, B9 value should be less than or equal to D9 value, and B10 value be less than or equal to D10 value. Now, there is also an option here, there is a thing called select a solving method, and there is a drop down. You could use simplex LP as the method that we are going to use to solve this problem. So, select simplex LP and that is what you get here. Now, you solve this problem to get the solution, which is x1 equal to 3, x2 equal to 2 with objective function is equal to 18. We have actually used this problem before, we have actually used keep the solver solution, and then we also get the sensitivity report for this problem. So, we have a sensitivity report for this problem which I have put. We have actually solved this problem before to get the solution of z is equal to 18. So, we have used this in an earlier situation. So, this is the problem that we have used. So, this is the problem that we had used earlier, and you observe that we have this solution here for this problem. We set the optimum solution, in this case it is a feasible solution, but the optimum solution is x1 equal to 3, x2 equal to 2, z equal to 18, and we said it is optimum. So, x1 equal to 3, x2 equal to 2, z equal to 18 is optimum in this example. So, we get the same example here with x1 equal to 3, x2 equal to 2 and z is equal to 18, which is the optimum solution here. Now, what also happens is we have this report called sensitivity report, and if I go back and zoom this report and make it bigger, now it shows a few things. It shows the values of x1 and x2, which are 3 and 2, which gives us the objective function value of z is equal to 18. You also have something called allowable increase and allowable decrease, which are actually the right hand side values can go up to an increase of 5 and a decrease of 2.5 for the same variables to be in the basis. But more importantly, now these are the right hand side, there are 3 constraints. Now, there is a description about the 3 constraints. Now, the first constraint is here. First constraint, the left hand side value is 22, the right hand side value is 26. The second constraint, the left hand side value, final value is 7 versus 7 and 11 versus 11 and 22 versus 26. Now, you can see this also here. 7 versus 7, 11 versus 11 and 22 versus 26. Now corresponding to this you see shadow price as 0, 1 and 1. Corresponding to this constraint shadow price is 1, corresponding to this constraint shadow price is 1, corresponding to the third constraint which is the B10 position the shadow price is 0. So if I go back to the Excel sheet you find corresponding to this shadow price is 1, corresponding to this shadow price is 1, corresponding to this shadow price is 0. Now this constraint the resource is not fully utilized, only 22 out of the 26 is utilized. So primal constraint is the resource is not fully utilized, therefore the shadow price is 0. In these two cases the resources are fully utilized, the shadow prices can be seen here as 1 and 1 corresponding to this positions 8 and 9. So those are the positions you can see corresponding to positions 8 and 9, the shadow prices are 1 and 1. The 7 into 1 plus 11 into 1 is 18, which is the value of the objective function. So when we use the simplex LP and go to the sensitivity report, we can also get the dual solution or solution to the dual of this linear programming problem. So just as the simplex solves both the primal and the dual, you can use this solver to get the solution to the dual also by looking at the sensitivity report. Now these are with respect to the right hand side values and how much the right hand side can increase for the same basis to remain and so on, but right now we restrict ourselves only to understanding the solutions of the primal and the solutions of the dual when we use this particular solver. Now let us move to a couple of other examples where we understand a few more things in linear programming. So to do that we go back to this. When we introduced, when we looked at the simplex algorithm, we looked at three situations. We said that we have a linear programming problem can give us an optimal solution, or a linear programming problem can be unbounded, or the linear programming problem can be infeasible. So we looked at examples for unboundedness and infeasibility, and we showed the graphical solution to this problem, and we said that this is unbounded, and we also said that if when we solved it by the simplex algorithm, we also said that when we actually solved it by the simplex, we said simplex indicates unboundedness by being able to identify an entering variable, but there is no leaving variable. So in this iteration we showed that there is an entering variable, but there is no leaving variable. There is an entering variable here, but you cannot divide and do that. Now let us take the same example that we used here, maximize 10x1 plus 9x2 subject to x1 minus x2 less than equal to 5, for x1 less than or equal to 24 as the problem, and see what happens when we solve this problem using the solver. So we go to this example. So let us look at this example. So we again have two variables x1 and x2. The objective function is written as 10x1 plus 9x2. So I can show those 10 and 9, I can write here 10x1 plus 9x2, and we can write the objective function as equal to 10 into the value of x. So objective function is equal to 10, objective function is equal to the value of x1 into 10 plus 9 into the value of x2, which is given by 69. The two constraints are x1 minus x2, x1 minus x2 is less than or equal to 5, 4x1 plus 0x2 less than or equal to 24. So, these two constraints have already been mapped here and the values are written here. So, now we call go to data and we call the solver. The objective function is already set to B5, the variables are set to B3 and C3, the two constraints are written here and we are going to use simplex LP and we solve this problem. So, when we solve this problem, you will realize that when in this box you read a message called the objective cell values do not converge. It has not given a solution. We will read a message which says the objective cell values do not converge. So, when you get a message saying the objective cell values do not converge, it means that the problem is unbounded. So, unboundedness is indicated by this message which says the objective cell values do not converge. So, now let us go to another example. Here when we did the simplex algorithm, we looked at another example where we looked at this particular example, which is to maximize 10x1 plus 9x2 subject to x1 plus x2 less than or equal to 5 and 4x1 greater than or equal to 24, and if we drew the graph for this, we said there is no feasible region and therefore the problem is infeasible. Now, we also said in simplex will indicate infeasibility by reaching the optimal solution to the new problem with the artificial variables. So, whenever we have such problems, we will have artificial variables. So, simplex will terminate, but the artificial variable will be present with a strictly positive value. Now, let us look at this problem and see what happens when we use the solver. So, maximize 10x1 plus 9x2 subject to x1 plus x2 less than or equal to 5 and 4x1 greater than or equal to 24. So, we look at this problem. So, again let me So, we look at this problem. There are two variables x1 and x2. Right now I have given values 4 and 0. So, we can give any value 2 and 1, let us say 2 and 1, and quickly we realize that if we look at this constraints, we realize that it is infeasible for the present value. The objective function is to maximize 10x1 plus 9x2. I have already written 10 into this position 2 plus 9 into this position 1, 29. Instead of writing 10 and 9 here separately and pulling it into the objective function, I have written the objective function as 10 into B3 plus 9 into C3, which gives the value 29. The constraints are written here, x1 plus x2 less than or equal to x1 plus x2 less than or equal to 4 here, and 4x1 is greater than or equal to 24. So, let us go back to this problem. The constraint was x1 plus x2 less than or equal to 5 and 4x1 greater than or equal to 24. So, I write x1 plus x2 less than or equal to 5 and 4x1 greater than or equal to 24. Now, we have written this problem. So, we want to solve this. So, we go to data and get the solver. Everything is already set. So, the objective function is here, the constraint positions are here, the constraints are drawn, and we use simplex LP. When we solve here, we will get a message that solver could not find a feasible solution. So, when we get a message solver could not find a feasible solution, it means the given problem is infeasible. So, this solver will give 3 messages. If it gives an optimum solution, it will say that optimum solution is found. For example, let us go to that situation where, let us take this example where the optimum solution is here. So, sheet 1, suppose I call this problem, again I go to data, I go to the solver and I solve it. It will say that solver found a solution. all constraints and optimality conditions are satisfied. If it gives that message, and then you have to read the solution to find the best value of the variables and the objective function. If it is unbounded, it will say cell values do not converge. If it is infeasible, it will say solver was not able to find a feasible solution. So, the three things that we discussed, every LP either terminates with an optimum solution, or is unbounded, or is infeasible. All the three cases are taken care of this way using this particular solver to solve linear programming problems. And as I also indicated, we could go back to the sensitivity report for this problem, the problem that we have been solving. So, if you write the sensitivity report, the primal has a solution x1 equal to 3, x2 equal to 4 with objective equal to 66, and we also see that the shadow prices are 2 and 1, you will realize shadow prices are 2 and 1. So, we go back here. So, 2 into 21 which is 42 plus 1 into 24 which is 66. So, the solution to the dual can also be found through this. In the next class, we will go back to some of the problems that we formulated, and then we show how the solver gives the solution to few of these examples. We did 8 problems in our formulation. We will try to see a couple of examples and show the solution using this solver.